this next section that we're entering in Math 20, quadratics. And Unit 3 deals with quadratic functions, and Unit 4 deals with quadratic equations. And quadratics is to Math 20 as linear functions was to Math 10. In Math 10, you're always dealing with linear functions and linear equations. 3x plus y equals 10 is a linear equation. Y equals 3x minus 5 is a linear function. So we're going to be focusing on quadratic functions. And we're going to dive right in today by learning about something called the vertex form of a quadratic function. And this is on page 1 of your unit handout. So what are we doing today? We're going to be describing properties of graphs of quadratic functions using terminology that's appropriate. Linear functions, that's Math 10. Linear functions, when you graph them, they're a line. That's why we call them linear. Quadratic functions have an entirely different shape, and that's what we're going to learn about first. And then we're going to learn about how we can take, I don't want to say any, but most quadratic functions can be created by taking this quadratic function and doing something to it. Okay, so you can think of that f of x equals x squared, and by the way, let's get this out of the way right now. You can think of this y equals x squared as being the mother of all quadratic functions. Every quadratic function can be produced from that quadratic function in some way. So, what is a quadratic function? Well, a quadratic function is any function that could be written this way. Now, there's a lot in here. This isn't just about looking at it and going, oh yeah, I get it. There's a lot of new stuff here. So this says that f of x, and I'm going to keep using f of x, but you need to remember f of x is y. F of x or y is equal to a multiplied by, in brackets, x minus p, quantity squared, plus q. It's very important for you to understand that f of x means y, but just as important for you to understand that a, p, and q have a name. They are called parameters. And we may have introduced that concept of a parameter in earlier lessons, but it's really important for you to understand that those letters are not variables. There's two variables in this equation that you're looking at in brown. One of them is x and one of them is y. A, p, and q are numbers. That's what I mean by parameters. So when you have the following quadratic function, y equals negative 3 x minus 2 quantity squared plus 8, a has a value of negative 3, p has a value of 2, and q has a value of 8. And those three parameters, those three numbers, tell you what the graph looks like, believe it or not. If you know those three numbers, you can construct the graph. And that's what we're going to be really focusing on today. So these things are called parameters, and really all they are numbers. Each quadratic function has a different set of parameters. Okay? You know what it's really like? It's like in grade 10 when we said this is a linear function. I hope you remember that linear functions can always be written this way. M and B are parameters. They tell you something about the line. M tells you the slope. B tells you the y-intercept of the linear function. Well, it's a little more complicated with A, P, and Q because there's no slope. Okay. This thing, and this is in your notes, this y equals a times x minus p quantity squared plus q is called the vertex form of a quadratic function. And by the end of today's lesson, you should understand why it's called the vertex form. You know how we can look at a linear function? And you can tell me the slope. The slope is 2. And you can tell me the y-intercept is negative 5. This is called the slope y-intercept form because it tells you that. This is called the vertex form because it tells you the vertex. There's some feature of a quadratic graph that we look at and we go, that's the vertex right there. That point is the vertex. And that point can be determined by looking at A, P, and Q. So all graphs of quadratic functions are called parabolas. Again, comparing things here, like last year in grade 10, all graphs of linear functions are called lines. They're lines. What is the graph of a quadratic function called? A parabola. Okay? It's a particular shape that we'll become intimate with in a minute. And as I said, the mother of all quadratic functions, the one that produces every quadratic function in the universe, is really y equals x squared. So we are going to familiarize ourselves in the warm-up with that function. So we're going to be looking at the features of y equals x squared so that we can change it to produce all these other functions. It's like the queen bee. It's going to produce everything else. Or the mother alien in the movie Alien. It's going to produce all of the other offspring. So, learning the terminology of quadratic functions takes us to the first warm-up. Sketch the graph of f of x equals x squared. Don't forget, I'm not going to do this every time. We have to grow and graduate beyond this. F of x is y. We're not going to write y equals every time, but f of x is another way of saying y. So I've got a table of values here, and I'm going to pick the values of x for us, and I'm going to pick -3, -2, -1, 0, 1, 2, and 3. These are kind of my go-to values of x if I ever have to make a table of values to plot a graph. By the way, this process we're doing here to graph this is going to be done once and only once. After this warm-up, you should be able to tell me everything there is to know about y equals x squared. Well, y equals x squared, so we square x. Well, when you take -3 and square it, I hope you don't need a calculator for that, you get 3. It's interesting that when we square the negative, it becomes positive. Well, interesting is maybe the wrong word. It's important to note that when you square the negative, it becomes positive. I still see the odd person putting into their calculator this. I don't know what to say at this point. I mean, you have to know that's wrong. We can't keep going back to this over and over again. -3 quantity squared means you have to square the -3. And I think we've had this discussion a number of times. If you're like me, I don't even put the negative in because I know I'm going to square it, right? Anyway, -2 quantity squared. Quantity squared, I don't know if anybody's ever explained that or you've ever heard it before. It means the whole thing. It means including the negative. Is 4, and then -1 squared is 1, and then we get 0 squared is 0. Now look at what happens here. We get 1, 4, and 9. And this is called symmetry in math. That there's kind of a middle here that's 0, and when you look this way and this way, you get the same result. And when you look a little further in one direction and a little further in another direction, you get the same result. Symmetry means it's like a mirror image. My hands are symmetrical. Okay? If I go from the tip of my nose over to where this thumb is, I will go the same distance to wherever this thumb is. If I go from this line down the center of my face to where this fingertip is, it will be the same as the distance to this fingertip from that line. And there's a line that goes down the center here. It's called the Axis of Symmetry. It's like a mirror is what it is. So let's sketch this. Let's plot the points 0, 0, 1, 1, -1, -1. So these points need to be points that you're familiar with. The bottom of the parabola is going to be at the origin. And when we go 1 to the right, it's 1 above. And when we go 1 to the left, it's 1 above. When you go 2 to the left or the right, it's 4 above. And when you go 3 over, it's 9 above. 2, 4, 6, 8, 9. Now, not everybody is an artist at sketching these things. Probably if I said sketch them now, sketch the curve, you'd probably end up sketching something that's quite pointed at the bottom. That's just the natural reaction. But it has to be curved at the bottom. And this lesson isn't about your artistic abilities. I'm just saying that it has a curviness. It's not pointed at the bottom. So I'm better at this on paper than I am on the smartboard, but basically it looks like this. That's not bad. And I can kind of cheat here, and I can tell you right now that I have probably got something that's got a bit of a point to it. So it's not that big of a deal. But this is what that overall shape looks like. That's not bad, actually. That's pretty curvy at the bottom. And this is what we call a parabola. Now, we do have graphing calculators, and you might wonder why we're making a table of values to graph something. That seems so 1970s. It does. It seems like, wow, we're actually making a table of values. It's because when we learn about P and Q, a table of values is helpful in figuring out what they do. Okay? But we could go, let's try this on the calculator, y equals x squared. And let's set up our axes to match what we have in our booklet. In the booklet, it goes from -4 to +4 for x. So when I go to my window settings, I'm going to choose window and go from -4 to 4. And then for y, it looks like my minimum y is -1 and my maximum is 10. If you're wondering what the scale is, that's just where it's going to put a tick. It's really unimportant. And then when I graph it, oh, now I turned my axes off because we were doing something in calculus in the last class. So let me turn my axes back on. When we graph it, this is what it looks like. And of course, it has a different kind of aspect ratio to what we've drawn because your calculator screen is not a vertical rectangle, it's a horizontal rectangle. So now we're going to go through the terminology. So the first term is the vertex. The vertex, which I'm going to call V, is at 0, 0. So what is the vertex? The vertex is this point. It's the point, in this case, that's the lowest point on the parabola. The axis of symmetry, let me highlight for you, first of all, by showing you with a highlighter what the axis of symmetry is. The axis of symmetry is a vertical line that splits the parabola into two mirrored parts. And it's usually drawn as a dashed or dotted line. And that line has an equation of x equals 0. Because every point on that line, x has a value of 0. You know, don't mess up your diagram, but if I said, what are the coordinates of this point? You would say 0, 8. What are the coordinates of this point? You would say 0, -1. Every single point on that line is x equals 0. Doesn't matter where it is vertically, x is equal to 0 there. So that's why the equation of the axis of symmetry is x equals 0. The domain, well, I know domain and range is not a friend to everybody, but we're going to have to really get better and better at it by the time we hit 30. The math 30, not age 30. Domain is all of the values of x that the function takes on. And this graph, although it is kind of pointing up, I hope you agree it continues to go to the left and the right. Like if I were to walk over to where x is 80, 100, does the graph exist at x equals 80 or 100? Yes, it's just going to be like really far away, but it's going to be there. So the domain is any number, and we write that in a couple of ways. We can write x is an element of any real number. This is just a fancy way, a mathematical, decorative way of saying, oh, x can be anything. We could say that x can be any number from -infinity to +infinity. And I don't know if you remember seeing that notation last year. You're going to see it more and more. This is not an x comma y thing. The round brackets mean it cannot equal negative infinity, and it cannot equal positive infinity. Okay, we'll get to another example of that in a bit. Now, what is the range? Well, the range are all of the values of y, but if you take a look at it, this is my eyeball. When I put my eye at y equals 0, I can see the graph. And when I put my eye above y equals 0, I can see the graph. But as soon as I just duck my head a little bit below y equals 0, ooh, my eye, what happened? As soon as I I've gone and buggered it up now. As soon as I move my eye a little bit below y equals 0, I cannot see the graph anymore. You understand that the vertex I've drawn is a big blobby dot, but it's actually just a really, really tiny dot. So how do we write that? We would say that y must be greater than or equal to 0. Y is always greater than or equal to 0. Y is never negative. Or we could write y is anything from 0 to infinity. How many of you, by a show of hands, do remember that way of describing domain and range with the brackets? I'm not asking if you remember 100% how it works, but you've seen it before, I hope. The square bracket, first of all, the two things that are given are always the minimum, then the maximum. So if I'm saying 0, comma, infinity, I'm saying the smallest value of y is 0, the largest is infinity. The square brackets are used to indicate that it can equal that number. And it can equal 0. Now we have this bit of business here. First of all, whenever you talk about a maximum or minimum, and this should make sense, we're talking about a maximum or minimum y. This graph, when you say minimum, it's the lowest point, right? Well, the lowest point is a reference to a vertical distance. How low you get is a vertical thing. So in this case, there is a minimum. It's a minimum value of y. And this is going to seem really goofy, but you'll get used to it. The minimum value is y equals 0. And the minimum occurs at x equals 0. So when you talk about where a point is, we talk about the x value. When you talk about what the point is, we talk about the y value. It's kind of a weird thing, but again, you will get used to it. And that's it. Does anybody have any questions with any of the terminology or that graph? All right. So now we're going to go through a series of warm-ups to figure out what those three parameters do to y equals x squared. To begin with, all of these parameters, I'm going to back up here just a bit and say that when we go from y equals x squared to y equals a times x minus p quantity squared plus q, these three parameters change the graph of y equals x squared. So when we multiply y equals x squared by a number called a, this graph changes. It's different. When we don't have x squared, but we have x minus some number squared, this graph changes. And the same with q. Those changes are called transformations. So a, p, and q are responsible for changing the original function of y equals x squared. There are three types of transformations that we are going to learn about today. One is called a stretch. I'm going to pause there and make sure you understand something. In mathematics, a stretch does not mean to make bigger necessarily. If I take the letter W, this is the original, I can turn it into the following, and that's a stretch. That's the new. This is the stretched one. I can take that original and turn it into that. And I'm going to adjust that slightly. And turn it into that. It's the same width, but I've squished it. That's still a stretch. A stretch can make something bigger or smaller. And although the stretches I've got up here are called vertical, we're making it taller or shorter, in Math 30 you will learn that there are also horizontal stretches. You could make something narrower or wider. So, stretches, reflections, and translations. And you will learn what all of those words are. So in these warm-ups, we're going to learn that basically, everybody, these two things are determined by A, and this is determined by P and Q. And I think even though you don't know what they do, I think it's important to start off knowing this is what's going to happen. When you put a number A into that vertex form, you get a parabola which is either taller or shorter, and you get a parabola which is either pointing up or pointing down because it's been reflected. And we have a lot to go through here, but don't look at it as some daunting task. We're going to learn from it and pick up the pace. So, what is the effect of A? When you look at y equals x squared, which we're going away from now, you're turning the page to the next page, and you look back at that y equals x squared, what does the graph look like if we graphed 2x squared? Or if we graphed 1/2 x squared? And I don't want you to draw anything just yet. We're not going to do a table of values here. Okay? I'm going to show you, though, that you should know what x squared looks like. Y equals x squared looks like that. You learned that on the previous page. So what y equals x squared looks like is this. Now what about 2x squared? I'm going to just show you a quick table of values here. When you calculated y and it was x squared, and you put a number like 2 in, you squared that to get 4, didn't you? But what if I said it's not x squared? What if it's 2x squared? We don't want x squared, we want 2x squared. Well, then you would take this 2, you would square it to get 4, and then you would multiply by 2 and get 8. And I want you to understand that it doesn't matter what value of x you put here. The value of y that you get on x squared has to be doubled to get the value of y on the new function. And we're not going to do a table of values. We're going to say that, I'll do some highlighting here for people watching on video, that this is that function, and if we double every y coordinate, this will stay the same. This one will be twice as far away from the x-axis, and this one will be twice as far away from the x-axis. If I'm multiplying all the old y coordinates by 2, everything gets pulled away from the x-axis. So that means that this is what it looks like. And, you know, for goodness sake, I don't care how well you draw it. I want to make this point to you. When a is 2, the parabola is narrower and taller. That's the point I want to make. How many of you suspect you know what 1/2 x squared will look like? Will? It'll be shorter and wider because all of those original y coordinates, instead of just going x squared and writing the y coordinate down, Like Will said, it's going to be shorter because we're going to take that original x coordinate, square it to get y, but before we write it down, we're going to multiply it by a half so it gets smaller. So all of these points are going to drop to half as far away from the x-axis as they were. And again, this graph that we're looking at, everybody, this lesson is not about you being able to graph these. It's about you understanding that when A is 2, it gets twice as tall. When A is a half, it gets half as tall. And if it gets half as tall, it's shorter and it will appear wider. And if it gets twice as tall, it will be taller and it will get wider. If I said to you, what do you believe? We can add one more. You don't have to write this. What do you believe y equals 0.1 x squared looks like? Well, 0.1 is a pretty small number. It's going to take all the y coordinates on the yellow graph, and it's going to multiply them by 1/10. It's going to be like this. Roughly, I don't know. I'm not going to get out the drafting tools and figure it out, but it's going to be pretty flat, isn't it? Correct, Kai. It will be flipped across the x-axis because the old y-coordinate is found by squaring x, but then this is multiplied by -1. So it's going to be upside down. Look, in other words, and I'm not going to worry about drawing this. This is all about understanding what we're seeing. This is x squared. This is negative x squared. It's upside down. So what do you think negative 2x squared would look like? Well, it would be upside down. And would it be taller or shorter? Don't let the negative mess with you. We're still multiplying by 2 somewhere along the way, which is going to make y coordinates bigger. They're going to be bigger in a negative direction, but negative 2x squared is the gray graph, and you can see it's taller. I would be perfectly fine if you just understood that. If you could draw the following, not even worrying about this grid, saying that if this is x squared, then this is negative x squared. This is about learning. This isn't necessarily about what you write down in your note package. The green one is x squared. The brown one is negative x squared. The red one is negative 2x squared. Now again, it's not very accurate because you can see that the vertex should still be at the origin, but it's negative x squared. And then it's stretched by a factor of 2. The green, I guess we've used green, so we'll go with the black. This would be y equals negative a half x squared. This is what's important, and I almost feel as though when I make the note package next time I should just remove the grid, but we need the grid for P and Q. Becomes important. So let's answer the third part here. What are the rules for the effect of A? If A is negative, then the parabola opens down. This is what we call opening down. Okay. If A is positive, then the parabola opens up. If A is bigger than 1, becomes taller. By the way, here's a perfect case of something that you haven't been taught yet, and I want to show you, but I don't want to get off track. I'm not talking about the negative, right? So when I say A is negative 10, forget about the negative. The A part is 10. It becomes really tall. And it will be upside down. And if A is between 0 and 1, so A is less than 1, then the parabola becomes flatter and wider. And again, I'm just talking here about, it's what we call the absolute value of A, not the negative part. Okay. So does anybody have any questions about what A does to a graph? Ultimately, I guess I should be able to give you 5 different values of A and 5 graphs, and you should be able to match them up with their A values. No questions there then. Okay, let's talk about P and Q. So what is the effect of the parameter Q in f of x equals x squared? So f of x equals x squared here, which by the way has an A value of 1, but it's not important. We're going to add something to it. We're going to change this to f of x equals x squared plus q. And the question is, what happens? What happens? That's what we're learning in warm-up 3. And rather than make a table of values, I've got all of these graphs in a program. We can decide what we're going to draw in a minute, but I want you to understand what's happening first. We know what x squared looks like, right? X squared is the y coordinate of the original graph. This second one, the y coordinate is x squared plus 2. So whatever y coordinate we get for the first graph, we're going to add 2 to it. Which means that x squared plus 2 will be this graph shifted up 2. And by the way, to how many of you do those shapes look not identical? They are identical. If you trace one, it will match perfectly on the other shape. The legend is up here. What's the next one? The next one is x squared plus 5. Well, look. It's pretty simple rule to follow. If x squared plus 2 shifts x squared 2 up, x squared plus 5 shifts it up 5. X squared minus 7, anybody want to take a wild guess, stab in the dark at what x squared minus 7 will look like? Jack?
The y-intercept will be at -7.
Right, so that red graph is going to be down at -7 for the vertex, which is the y-intercept. And x squared minus 3 will be down 3. I feel as though I don't even want to spend time drawing all of these, but I will draw a couple. And I'm not going to spend too much time on this. Y equals x squared looks like this. And I can very easily cheat. If that's y equals x squared, then this is y equals x squared plus 5. Shifted 5 up. This is y equals x squared. This is y equals x squared plus 5. I'm going to do one more. Let's do the x squared minus 7. No, we'll do minus 3. This would be y equals x squared minus 3. Pretty straightforward. So this is called, by the way, a translation. I think in junior high you called them slides. Does that ring a bell? It does for a couple of you. What are the values of q? Well, q here is 0. There is nothing that we're adding. Q is 2, Q is 5, Q is -3, Q is -7. So notice that if Q is positive, it moves in a positive y direction. becomes more positive vertically. If q is negative, it moves in a negative y direction. And that's what we're going to conclude. What is the rule? If q is positive, it shifts up q units. If q is negative, it shifts down q units. And again, you haven't learned this thing called absolute value yet. But when I say it shifts down q units, this is not including the negative. One of our examples, we had q equals -7. Am I right? Okay, we wouldn't say it shifts down -7 units. We would just say it shifts down 7 units. That's my point. All right. Finally, what's the deal with p? So what's going to happen here, everybody, is you're going along nice and smoothly, and many of you are going to start to stumble at this point because there's something weird happening with p. We're talking about going from y equals x squared to y equals x minus p squared. And the question is, what happens? That's the question. So let's forget about p for a second. And let's take a look at the functions. We have x squared, and then we have, let's take x plus 3 squared. Let's take a look at the graphs of these two functions. And as we do this, I've explained to you why a does what it does, and I've explained to you why q does what it does. I'm not going to explain to the class why p does what it does. Okay? If I asked you, let's take a look at these graphs. Here is y equals x squared, and I'm going to toggle now y equals x plus 3 squared. I know that everybody in the room knows in their head what the graph is going to do. And I won't put you on the chopping block and ask you to stick your neck out for this. Would you agree, though? Most of you would say it moves 3 to the right. Well, guess what? It moves 3 to the left. So first of all, it has something to do with left-right because that number is not being added to the old y coordinate. It's being added or subtracted from the x coordinate. But it moves in an opposite direction to the sign. So be careful about what you conclude because we're not done here yet. Do you agree it does move 3 units to the left? So if it's x plus 3 quantity squared, it moves 3 units to the left. What do you think x plus 4 quantity squared will do? Well, 4 units to the left. That makes sense. And again, the legend is up top, so you can look at these. And I'm really leaning next time towards not even having us graph on paper. We can learn this by looking at it. And I think, let me get rid of these now. I think you would then suspect that x minus 5 shifts to the right 5 units. And look at that, it does. So and for completeness, x minus 2 shifts 2 units to the right. Let's over here in our notes make a note that x minus 2 shifts 2 units to the right. X plus 4 quantity squared shifts 4 units to the left. You're getting the pattern here. If it's x minus, it shifts to the right. And if it's x plus, it shifts to the left. Okay. When it was x minus 5, it shifted to the right 5 units. And when it was x plus 3, it shifted to the left 3 units. Now comes the question, though. And I'm not even going to get us to graph these. Okay? I'm going to get rid of this entirely. And I'm going to take a look at y equals x minus 2 squared. we know it shifts 2 units in a positive direction. Okay, let's just take a breather here. In terms of x, to the right is positive, to the left is negative. Okay. When you compare this to y equals x minus p quantity squared, I want everybody to figure out what is the value of p. So what number would I put for p right here so that we get y equals x minus 2 quantity squared? It's not a trick question. You'd put 2 there, wouldn't you? So p is 2 for this function, and 2 is a positive direction. It's a positive number, and that's why it shifts to the right. There's a deep underlying reason why this happens. But the bottom line is we write x minus p so that if p is positive, let's see if you can follow this. If p is positive, then it will be x minus a number which we've learned shifts to the right. That's pretty greasy. You wrap your brain around that and you think you have a good handle on it, and then all of a sudden it slips out of your grasp. Let's take a different one. Let's take x plus 3 quantity squared. So we have y equals x minus p squared. This is our template. This is what we always want to compare everything to. And we compare that to y equals x plus 3 quantity squared. What is p? What number would I put in for p into x minus p squared to get x plus 3 squared? Lucas? I'd have to put in negative 3, because then it would be x minus negative 3, and minus a negative is positive. And that means that p is negative here. And look at the direction it was shifted. It was shifted to the left, which is a negative direction. The value of p in x plus 4 quantity squared would be negative 4. The value of p in x minus 5 quantity squared would be positive 5. This is what I mean by stumbling. I want to go back and talk about q. Remember we said if q was positive, it shifts in a positive vertical direction, which is up. If q is negative, it shifts in a negative vertical direction, which is down. Well, with p, if p is positive, it shifts p units in a positive direction, which is to the right for horizontal. And in case you haven't clued in on it, I think you have, q has to do with moving up and down, p has to do with moving left and right. And if p is negative, then it shifts p units in a negative direction. Of course, when I say p units in a negative direction, which is to the left, I mean don't include the negative when you say p units. If p is negative 5, it just shifts 5 units to the left. So now you know what A, P, and Q do, and the lesson now can be concluded by looking at examples where we put it all together. And this is going to require practice, and I will tell you right now that on Thursday we're going to have a quiz. We're going to come in Thursday, we're going to go over the work that's assigned today, and we're going to have a quiz after that. So in order to sketch any graph, you need to know A, P, and Q. Let's take a look at some of these. For each function, do all of this. All of it. Okay. I'm going to ask you a series of questions. Well, let's start off with, I want you to write down what A is equal to, P is equal to, and Q is equal to. You are comparing always to y equals A, x minus p squared plus q. And by the way, that's on a formula sheet, so you don't have to memorize it. I want you to write down what A is equal to, P is equal to, and Q is equal to. And it may very well be the case. I'm just looking at the clock right now. We had that interruption. It may very well be the case that we're going to continue to work on this for the first part of Thursday and then have a quiz at the end of the class. Okay, we'll see. I don't want to rush it. This is really important. If we spend 2 days on this lesson, so be it. A is equal to 4, P is equal to 7, Q is equal to 6. Would you agree? Okay. So here's the series of questions. Will this parabola open up or open down? Zoe, what do you think? Will this parabola open up or down? It will open up. Why is that? Right, because A is positive. 4 is a positive number. So it's going to open up. Will this parabola, Zoe, be the same height as x squared, or will it be taller or shorter? This is our first question, so we're putting this all together. It takes time. It will be taller. It'll be 4 times taller because that value of A stretched things by that factor. So don't draw anything just yet. If I said to you, what does y equal 4x squared looks like? Don't draw this. If this is x squared, then 4x squared looks like this. And remember what I've told you. I just care that you know that 4 makes it taller. Okay. Look at where the vertex is right now. The vertex is at 0, 0. This is just for reference. We don't need that. The vertex is at 0, 0. Next question. And again, you're not necessarily graphing this. Grace, will this graph shift up or down? It will be up because Q, which is the vertical shifting parameter, is positive. It shifts in a positive direction. We're going to have to shift this thing. So this makes it taller. We're going to have to shift this 6 units up. McKenna, will that 7 shift it to the left or the right? To the right, correct. And this, if you said left, that's okay. Everybody's going to stumble from time to time. Because this parameter is positive, it shifts in a positive direction. So it's going to shift 7 units this way. Which means, everybody, if we shift 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6. Then the vertex is going to be at 7, 6, isn't it? That's going to be where the vertex is, which is P, Q. The vertex will always be at P, Q. And we'll see that it doesn't matter if these numbers are negative. So the vertex is at 7, 6. The axis of symmetry where's the axis of symmetry? It's this line. That's at x equals what? 7, right? The vertex is always going to be at P, Q. The axis of symmetry will always be at x equals P. Does this have a maximum or a minimum? Jack. It has a minimum. Can you tell me, and I don't know if you'll remember the exact details of how this needs to be answered, but this has a minimum at what? There's a certain way we say it, you know?
At or equal to
we don't even need to say or equal to 7. The minimum occurs at x equals 7. The minimum value is y equals 6. So the minimum value refers to y, where it occurs refers to x. We're also asked for the domain and range. And again, I would much rather go slow and maybe not even finish this lesson today than to rush through in the next 10, 12 minutes. The domain, look at this. We've already talked about that. It becomes taller. It moves 7 to the right and 6 up. It opens up. We've already addressed that. There's a minimum value. Oh, we got to do domain and range. The domain is x is any real number. And I hope everybody sees, I don't care what you do to y equals x squared. The domain's going to be any real number. The range would be y is greater than or equal to, if there's a minimum, y will be greater than or equal to some value. Well, what's the minimum value? The minimum value was 6. So y is greater than or equal to 6, which is q. It will always be that way. Now, be careful. If it opens down, then the range will be y is less than or equal to that number. Taking care of that. We've got the vertex. We've got the equation of the axis of symmetry. We've got a pretty decent graph. For the remainder of these questions, everybody, I'm not going to worry about drawing x squared. Okay? How much taller it gets or how much shorter it gets is a matter to be discussed in Math 30-1. Just saying it's taller or shorter is what we deal with here. So let's take a minute, and I want everybody to write down what a, p, and q are equal to. Remember, you are comparing the function to y equals a times x minus p quantity squared plus q. Pretty straightforward. A is negative 1/3, q is 7, p is negative 4. So this is the thing you have to get used to. P is the opposite of the number you see with x, because x minus negative 4 will give you x plus 4. Lucas, will this open up or down? Down. Why? Because a is negative. Will it be taller than x squared or shorter than x squared? Actually shorter. Because neglecting the negative, a is a third. So it's going to become 1/3 as tall. Remember, if a is big, it gets bigger. If a is small, it gets smaller. And by the way, we're comparing it always to this. So is 1/3 bigger or smaller than 1? It's smaller, so the graph gets shorter. So the graph is going to have a shape. Before I slide it around, it's going to have a shape that looks like this. It's going to be quite flat's the wrong word, but spread out and wide because of the third, and it opens down. Declan, will this then be shifted to the left or the right? Excellent. How many units? 4. And then which way will it be shifted vertically? Up. How many? 7. Good. And it's up because even though I didn't write a positive, there is a positive here. So we want to try to, I know you have to sketch the graph, but we want to try to become good at abstract thinking here. And the vertex is going to be negative 4, 7. I haven't sketched it yet, but look at where the vertex is now. And if I shift it 4 to the left and 7 up, then it will go to negative 4, 7. Before I graph it, if I talk, for example, about the axis of symmetry, Don't abbreviate this on an exam, but the axis of symmetry is going to be at x equals -4 because the center of that parabola will be at x equals -4. Before I sketch it, you should be able to figure out that the range is y is less than or equal to 7. Because it opens down, the y coordinate of the vertex is the biggest value of y, and then it bottoms out on both sides. I'm going to actually now sketch this. We move this 4 to the left and 7 up. So this is at -4, this is at +7. I think the only thing we have, well, domain, x is any real number. The only thing we have left is the description of the minimum or maximum. And we have a max of y equals 7 at x equals -4. Again, that seems kind of weird to have those rules, but it's what we do. That was B. We have 2 more. So what I'm going to do is work with you on C, and then to close out the class, I'm going to ask you to do D, and I'm going to assign a couple of questions to have you complete for Thursday. Okay? Okay, I would like everybody to write out the values of A, P, and Q. This time I'm not going to write down the template. You could look on your formula sheet for the template, by the way. Did I take attendance? Yeah. 1, 2, 3, 4, 5, 6, 7. Okay, that's good. Logan, what's A? 0.2. So let's start with describing what A does to y equals x squared. Will this parabola open up or down? Up, good. Because A is positive. Will this parabola be taller and narrower, or will it be shorter and wider? Right. Because 0.2 is less than 1, right? It's actually 20% of 1, which means it's going to be 20% as tall. So before we shift it around, it's going to look something like that, right? Leighton, what is the value of P? 3. And what effect will P being equal to 3 have on y equals x squared? 3 units to the right, good. So I'm not writing down the effect of A. I've included the effect of A by showing the flat graph. But I am writing down that it goes 3 units to the right. And Lily, what is the value of Q? Excellent. So Q has a value of -8. And Lily, what effect will that have on y equals x squared? Down 8 units. Excellent. So this is what I mean by not including the negative. You wouldn't say it goes down -8 units. You'd just say it goes down 8 units. So the vertex will be at 3, -8. And again, I keep coming back to this, that the vertex is at P, Q. I mean, you shouldn't even really need a graph to see that, because P is the horizontal shift, Q is the vertical shift. The vertex will be at 3, -8. Won't put anybody on the spot for some of these other things, but I want you to write down what you believe the range is. Well, in this case, it's y is greater than or equal to -8. It's greater than or equal to q. Why is it greater than or equal to and not less than or equal to? Jack?
Because it's curving upward, so it can't get less than -8.
Right. If there's a minimum, your range will be y is greater than or equal to q. And by the way, that means if a is positive, it will be y is greater than or equal to q. If a is negative, it's going to be y is less than or equal to q. The domain is any real number. The axis of symmetry will be at x equals 3. Let me draw that in. This is the axis of symmetry. What do we put for the minimum? We say there's a minimum that happens at 3, and the minimum has a value of -8. Or you could just put it together in a cleaner, more succinct statement and say the minimum is -8 at, I don't really like that. The minimum is y equals -8 at x equals 3. I think you need those y's and x's in there. I want to just say the minimum is -8 at 3. I think that's sloppy. You know, this is the goal that you should be able to look. I'm not even going to worry about 1 and 2. You should be able to look at stuff like number 4. And I think I'm going to say that number 4 will be homework. Not, practice it if you want. This is your assignment. You should be able to tell me, even if you don't graph it, without using a graphing calculator, you should be able to tell me the domain, the range, is it a max or a min? Where does it happen? What is it? What the axis of symmetry equation is? Where's the vertex? Does it open up or down? You should be able to tell me a grand story about each of these without using a graphing calculator. In fact, I'm not even going to assign example D. I'm going to say this is your homework for Thursday. I know there's not a lot of time left, but see if you can just get one done. It shouldn't take you that long. Look in the back and see if you're right. Was that okay, you guys? Rushed? I always want you to be honest. It wasn't? Too slow? It was Goldilocks, just right. Perfect.